of this study group. Yeah, so we're just the study group is kind of an informal study group where we're going to go over a bunch of papers from from diffusion model literature and discuss them, and I guess ideally folks would prepare some sort of quick presentation, some presentation to go over that, and then we discuss different aspects of the paper. So that's kind of, yeah, I guess here is a little bit more information about what I had planned. It's a weekly study group, and I guess we'll assign papers. So for this week, we had the DDPM paper, and depending on how things goes, we maybe just read one paper. Maybe that one paper might take more than 1 week, or we might be also reading multiple papers. So it just kind of depends on how the project is going and how everyone's feeling. So right now, just for now, we just wanted to start out with this DDPM paper, since that's a kind of a fundamental paper, and then maybe in the future we'll do more than one paper. We'll see. And then yeah, I guess one person would ideally present would present the paper. So I'm presenting this week, and then we'll see about maybe the following weeks. We'll just discuss and see. And yeah, I'll try to prepare some like a collab notebook or something, because of course having the code is also really helpful just to see it from that perspective as well. So I'll see if I can have something prepared by next week for at least this DDPM paper. But so no guarantees, but that's kind of that's what I'm planning. So we'll see. Or also if someone else wants to help out and contribute some code as well, that would be helpful. Let me know if you're interested. And then yeah, the meetings will be recorded. So I guess if you're unable to attend a particular day, it'll be available. And I'm planning to put some of these resources on GitHub or some place, I guess maybe in the chat or something like that. And I guess hopefully anyone in the future who's also presenting can do so as well. And of course, feel free to ask any questions or interrupt at any time, because yeah, we're all here to learn. And if you have any confusion or any questions, it's best to address them as soon as possible. So yeah, I guess any questions about that?
How much time did you want to allocate to each session? It's like right now, I don't think we set a time.
Yeah, good question. So I'm planning right now to allocate 1 hour, and I guess at the end of this 1 hour, we'll see how we feel. Yeah. So right now we have 1 hour, and then yeah, we'll just kind of see how we feel, and if we are on board with more time, that's fine with me too. But right now, I think the schedule is 1 hour. So yeah.
Okay.
Yeah, and then also I'm very happy that Catherine was able to join as well. And she's the expert here who I guess yeah, it'd be it's very great to have her expertise, and she can correct me if I'm saying anything wrong. So yeah. Okay, so if there are no other questions about this, I guess I think yeah, I'll get started with the DDPM paper. I guess I just want to know, did everyone get a chance to read it? I guess if you didn't, do you want to? I guess yeah, because it's totally fine if you haven't, because I'm going over it anyway. But just wanted to make sure how everyone is feeling about this paper so far.
I'll break a bit of the silence. I tried to go through a bunch of it, and I feel like it's going to be great to go through it with other people.
Okay, that's good to hear. Okay, yeah, it's definitely a little bit of a mathematically dense paper, so I completely understand
I've been over this paper many times, and there's still parts of it that I don't fully understand.
Okay.
It's great to feel that I'm not alone.
Yeah. Okay, so with that said, I'll get started with some background about, I guess, generative models in general. I guess the task of all generative models is to attempt to estimate the data distribution given some observed samples, and just given that we have some samples of the data, try to estimate the distribution so that we can later on sample from that distribution and generate our own samples as well. So there are two kind of main approaches that have been very successful, I guess, over these last few years. There's some that are known as explicit likelihood methods that would include things like variational autoencoders, normalizing flows, etc. So variational autoencoders were, quite popular early on, but then later on, of course, we saw other models like generative adversarial networks that were much more popular, and those are sometimes referred to as implicit likelihood methods. And with the generative adversarial networks, of course, we saw just amazing samples coming out from those very high quality samples. And you've seen, like, for example, the generated faces and all these sorts of images with StyleGAN as well. So it's very clear that the generative adversarial networks were able to produce these great quality samples, but of course they had their own challenges in terms of training was unstable and other issues as well. And one way of, I guess, approaching this sort of these sort of models is kind of classifying them according to these sort of properties as well. And sometimes this is called as the generative trilemma, in terms of you could have these different properties in terms of having a high quality sample, mode coverage and diversity of the samples, as well as fast sampling. In terms of the GANs, you're able to get the fast sampling and the high quality samples, but often you had this sort of mode coverage problem where you wouldn't be able to, I guess, you would have like less diversity. You'd have this problem of mode collapse where you'd only be able to get, you'd get very similar outputs, and you wouldn't be able to get a wide diversity of samples. And some of the like VAEs and normalizing flows were able to improve on the diversity. And there, of course, but the quality of the samples weren't that great. So what we'll see with the diffusion models is that you are able to get this sort of diversity, but also you are able to get high quality samples, which is why these diffusion models are very attractive. But as you can see, with a lot of these models, you're only able to get two of these components. And we'll see with the diffusion models, one of the main issues is the sampling. And of course, there's been a lot of work to improve the speed of the sampling, but that is definitely a challenge in terms of diffusion models having a low sampling. It's kind of slow sampling with diffusion models. So that's kind of another interesting way of summarizing it with this generative trilemma in terms of providing the context for all the different models. So with that said, just another brief summary of diffusion models before. Oh, sorry, someone's going to say something? Okay, thought I heard someone was going to say something, but okay, I'll move on. Just a brief summary of diffusion models in general before we dive into the DDPM paper. Originally, diffusion models were actually introduced in all the way in 2015 by a paper by Zoll, Dickstein, et al. And yeah, that was the first paper, but it wasn't very, I guess, people weren't really, I guess, utilizing the method or paying attention to the method until 2020, where we saw this DDPM paper. And this was kind of the first demonstration of high quality samples being produced by diffusion models. And so that kind of set off the whole rage with diffusion models, and everyone started looking into this and improving with diffusion models. And basically, it's the short summary of how diffusion models work is that it's basically kind of a denoising method, where actually we're just kind of starting out from noise and denoising from pure noise. And we're doing this in an iterative fashion. And as we'll see later on, you'll see later on that this is kind of equivalent to sampling from the estimated data distribution. So that's, in a nutshell, that's what diffusion models are, just sort of this sort of iterative denoising algorithm that we are training, but that allows us to produce these sorts of high quality samples. And of course, this is still a very new field. Again, it kind of only this field kind of only started out in 2020, and since then it's just exploded a lot. But there's still a lot of interesting work to be done in the field. So yeah, any questions about that before we delve into the DDPM paper specifically? Okay, there are no questions. We will dive into the DDPM paper, which is this milestone paper, this landmark paper, published by Jonathan Ho et al. And basically, I guess we'll just dive right into the details of the model that they described, where let's just, I guess, dive in directly. So of course, the model was developed for generating images. So we're going to talk about everything in terms of images, but obviously, as we'll see later on, we can expand this to not only images but other forms of data as well. But basically, I think it's worth starting out with some definitions in terms of the notation and what these different notations are referring to. So yeah, starting out, we have, of course, let's see if I can have a laser pointer or something in here that can help me point to things. Yeah, here we go. So starting out, we have the original image that is kind of our, I guess, the images that we are observing, whatever samples that we already have. And we're denoting this as x0. And then what we do is we are going to have this noise adding process, that we are adding noise to this image that we have. And we continually add noise until we get a final, I guess, image, which is just pure noise. It's a final Gaussian noise. So we have some sort of Gaussian noise, and that's what's referred to as xt. And of course, t is referring to basically like a time step. So we're going from x0, and this is an iterative process where we're adding noise iteratively. So for each time step, we are adding noise. So that's what the t is referring to, and the capital T is the final time step. And so we have this, what is known as a forward process, where we are starting out from x0 and iteratively adding noise to finally end up with xt. And this process is a Markov chain. And I don't know how familiar some of you guys are with Markov chains. I think maybe a lot of you might be familiar, but just to kind of refresh your memory, it's basically a stochastic memoryless process. And what that means is that we are just dependent on the previous time step. So if we want to go from x1 to x2, of course, that only depends on x1. If we just want to go from any sort of xt minus 1 to xt, it only depends on xt minus 1. We don't need any of the previous time steps, just the last time step in order to produce the following time step. So that's what is referred to as a Markov chain. And so that's what we have with the forward diffusion process. And of course, we have our intermediate time steps, where we have our intermediate images. And so, of course, these will be noisy, I guess, at different levels. So x1 will be just a little bit noisy, whereas if you're going all the way to xt minus 1 over here, that'll be a very noisy image. And so the noise level in the image kind of increases as we are increasing our time step. So yeah, that is the forward process. And in terms of the forward process, we have a distribution that we can define and sample from to produce the next time step. So here we have a distribution, and as you can see, it's just dependent on the previous time step, and which is why it's a Markov chain. And we can define this distribution and sample from this distribution. In this case, this is just a simple Gaussian distribution. So it's pretty trivial to be able to sample from a Gaussian distribution. And here, basically, the Gaussian distribution has a mean. So this over here is the mean of the Gaussian distribution, and this is the variance of the Gaussian distribution. So we have the mean, which is kind of parameterized by the previous time step, kind of scaled by this factor here. and then we have our variance as well. So we have our variance, and the variance has a predefined schedule. So this is schedule for the variance, which of this, and we have this predefined variance schedule. Of course, the variance starts out low at the beginning, which means it's not really adding much noise. And then as we move along with higher time steps, the beta t increases and we add more noise to the image. So we have this Gaussian distribution that we can sample from, and all we're doing with this Markov chain forward process is we have this predefined Gaussian distribution and we just sample from it, starting out from our original image and continuing all the way to the end of the distribution of the Markov chain to get our x capital T. So yeah, we have here an example of that, where I have our x0 and we just continue along to get our x capital T. So that is the forward process. Hopefully that makes sense. If there's any confusion about the forward process, please let me know now. Okay, if there's no confusion about the forward process.
I'm a little bit curious. I don't know if you can speak to this, but like how the variance schedule, like the sorts of ways in which it affects the learning, like the sort of theoretical grounding of like why you would want to schedule it one way or another.
Right.
I feel like it's one of the elements that I don't really understand.
Yeah. I think we'll probably talk about that later, but yes, that does affect, well,
So far as I know, the schedule isn't like theoretically grounded in any real way that I know of. And it's all just like empirical as to which schedule produces the best actual results, usually measured in terms of FID.
Cool, thanks for that.
So yeah, okay. Any other questions about the forward process?
Hey, this is Hakan. What's the n supposed to be?
That's the normal distribution, Gaussian distribution.
Okay. Thanks.
Yeah.
It's something quite close to a normal distribution, but not fully a normal distribution, but is close enough to the point where you can sample from a normal distribution to start the reverse process, and it's supposed to match sufficiently well that the small gap isn't relevant.
Yeah.
Yeah.
Well, I guess
actually...
also.
Oh,
Go
sorry
ahead.
about that.
Go ahead.
I was actually curious about that because obviously a normal distribution sort of has those infinite tails. Like, does it just end up getting clamped for the image values along the way?
Nothing's clamped, so.
Or I guess it has to be. Well, because like I know there was like some discussion. This is actually, to be honest, this is a part that I was a little bit confused too. A little bit was like I know, like I guess at the end of the step of the, I guess of the inference or the sampling, for I guess the reverse distribution, I guess there does need to be some sort of binning of the values to get, I guess, the discrete values. But I'm not. I guess yeah. When we get to that part, maybe Catherine can talk about that a little bit more.
Mm-hmm.
Yeah, but I guess when we're starting from the forward process, we just use the values and do it appropriately. And then I guess the values can be continue. It doesn't have to be discrete when we're doing the forward process. But then I guess with the reverse process, I guess at the end you do have to have that, I guess, binning or whatever to make it discrete, to get a discrete image out of it. But yeah, when we get to that, we can talk about that. Any other questions? Okay, if there are no other questions about this, then I'll move on. Or is there something in the chat? Also helpful to see in the Markov process that we're scaling the image down to 0 in addition to adding the noise. Yes. Okay. Let's see here. Nothing there. Okay, so some properties of the forward process that turn out to be really helpful. So since the forward process is a Markov chain, the following statement holds true. Basically, since each of these distributions are, or each of these are conditional distributions that are independent of each other, like for each variable, it's just dependent only on the previous one. For each time step, it's only dependent on the previous one. Then we can just multiply them out to get the distribution for the full for like the end time point. So basically just dependent from x0, and then you can get xt from that. And so just because it's a Markov process, everything is independent. And then since the distributions are Gaussians, you can actually do a little bit of math to get actually at any arbitrary time step Gaussian distribution. And this Gaussian distribution, of course, you have the variances. You have to calculate the variances out. But apart from that, again, because it's all independent, you can just get a Gaussian distribution. You can define it, and what that means is that you can sample a xt for any arbitrary time step t. So you don't have to, like, for example, go through each time step and calculate out each time step to get whatever time step you want. But you can just go and calculate the time step directly because of the properties of this being a Markov chain and the properties of it being a Gaussian distribution. Okay. So again, just to clarify, beta t is these are all constants that are predefined. So these are all just basically constants that we already know. Okay, so the next thing is the reverse process, where we're doing the reverse of the forward process, where we're going from x capital T, which is our pure noise, to x0, which is the image that we're trying to obtain. So again, here we're doing a Markov chain with Gaussian distribution transitions. And again, so basically it's of a similar form where we have this conditional distribution dependent on the previous step. So the previous step would be xt. So we have xt minus 1 dependent on xt, because we're going now from, I guess, capital T down to 0. So it's in the reverse, so it might be a little bit confusing, but that's why we have xt minus 1 dependent on xt. And there we have our normal distribution, and we have our mean and our variance. But the important aspect of this is that this is learnable. These are learnable functions that are actually neural networks. And what we're doing with this whole diffusion model is we are training these neural networks in order to give us these Gaussian transitions so that we can go from xt to x0. So once we train our model, then we can just sample just in the reverse with our Gaussian transition. Does that make sense? So that's kind of the setup of this reverse distribution process. And now what we're going to discuss is what is the appropriate loss function to be able to get us these neural networks that we are training to get us the reverse diffusion transitions. Okay, if that makes sense, I will move on to discussing the actual training and the loss function and all of that. So of course, the whole general idea here is that we want to find optimal parameters for our function that maximizes the likelihood of our training data. And so in order to do that, of course, what we want to do is we want to minimize this negative log likelihood term. But of course, this is not tractable directly to optimize, because in order to basically, we're having this function here, which is the negative log likelihood of the probability distribution of our images, and that is dependent on these time steps or these latent variables. So if we wanted to get this function, we have to marginalize out those latent variables. So that means you have to integrate over all possible values of those latent variables, which, as you can imagine, is intractable to be able to do that over all possible values of the latent variables. So directly optimizing this log likelihood is not possible. And this is basically true. This is basically how we have these latent variable models set up. And this is like true, for example, for variational autoencoders, which I'll discuss a little bit later as well. So this is a similar setup in that respect. And in fact, yeah, actually, I guess I'm doing that comparison right now in terms of comparing it to a variational autoencoder. Basically, in a variational autoencoder, you have your images, but then you have this latent variable, and you have sort of this probability distributions, conditional distributions from going from the image and giving the latent variable, or given the latent variable, can we get the image? And that's what the variational autoencoder setup is looking like. And then with a hierarchical variational autoencoder, you may have multiple latent variables, and you have similar, I guess, probability distributions that we're trying to learn going between these different variables. And in comparison with the diffusion model, it's a similar sort of setup, except we have a fixed forward process. So when we're going from, I guess in this case from left to right, where we're going from x0 all the way to xt, that's fixed to this sort of Gaussian transition, as opposed to with the variational autoencoders or hierarchical variational autoencoders. Those are also learned functions that we have to train. So there is a lot of similarity between the diffusion models and the variational autoencoders in terms of their setup. And so, yeah, just kind of to summarize that, a diffusion model can be considered as a hierarchical variational autoencoder with a fixed Gaussian encoder, which means that we can leverage a lot of the sort of setup that VAEs use for training them, and we can apply them to diffusion models as well. So yeah, I think this was maybe a little bit of the kind of where maybe some of the confusion might start in terms of how this is set up. We have this sort of elbow loss, which is again a trick that is taken from variational inference, Bayesian inference, and is used for VAEs as well, where we have this sort of this sort of inequality, and instead we are training this other term instead of directly training the log likelihood. And so that's what we have, this elbow term. So I think there was some confusion about how this elbow term works and all. Maybe this is a good point to stop, and I guess if people had questions about this. Oops. Are you telling me this is perfectly clear? I don't believe it.
So, I mean, I guess it's somewhat understandable, right, that the other one is so hard to actually compute. So this is just a technique that you can use to get a sort of approximation that you can also minimize, and so it's more or less the same thing.
Right. Basically, I mean, it's basically the same setup as a VAE. It's just that you do have this fixed Gaussian encoder. So as we will see, because of that fixed Gaussian encoder, we can make a lot of simplifications from a standard hierarchical VAE setup.
I'm not sure if you have you may not have the slides prepared, or have it prepared, but is there any way that you could go into how elbow emerges from KL divergence? I always have trouble with drawing that relationship.
I mean, I do have, for example, so there's like multiple ways of deriving this. elbow loss, I do have one slide that shows one way of deriving it. Where is that slide? Like this is one way of deriving it where it's just, I mean, this is just kind of, I guess, math. And then there's this sort of what's known as the Jensen's inequality, which is the last step. And that way you can take the sort of inequalities, what takes us from just, yeah, that allows us to get us the elbow loss. Then I think there was another derivation that was in, yeah, I can see if I can find, there's like one of the links. Let's see here. So I'm sharing my screen. I think, where was it? Actually, I think it may have been from that tutorial that was shared just a couple of days ago. I was actually looking at it earlier today. Where was it? This was in reference to elbow hierarchical. No.
It starts at equation 9, like the derivation. So yeah, right there.
Yeah, here. So this might also explain this a little bit better compared to what I'm doing here. But basically, what it was showing, where was it? Just kind of orienting myself here. So yeah, so we have this, and then basically, yeah, what it's saying is that what the Jensen's inequality was doing is basically showing that basically we can take this sort of log. So yeah, we have our log. Sorry, I'm just trying to. Yeah, the log of the probability distribution, and that is essentially equal to, yes, that's what the step is. That is essentially equal to this KL divergence term plus the elbow. So what it's saying is that the KL, yeah, basically what it's saying is that if you are minimizing if you in this case you're maximizing the elbow, there's confusion there because technically you maximize the elbow and then minimize the variational lower bound. I think it's just like a change in the sign. But anyway, they're saying here that if we want to optimize it so that we're matching the true distribution, which is by minimizing the KL divergence, that's equivalent to maximizing the elbow term because the sum must stay the same. So if we're maximizing the elbow term, then we're minimizing the KL divergence. So, yeah, that's what they're saying here. So again, the next slide I was going to show is about KL divergence. The KL divergence is basically a comparison of two probability distributions, and if the KL divergence is minimized, that means that those distributions match. So this is sort of a proxy for minimizing, this sort of matching of the two distributions using this elbow term. So that's what kind of is going on. Does that make a little bit more sense?
Yeah, absolutely.
And this link is also in the chat, so in our thread, so you can also check it out later as well and read it for yourself. And yeah, I actually like the section on the variational autoencoders and stuff. It was a good explanation, I think.
Yeah, thank you. I definitely agree.
So yeah, going back here, so that's what we're talking about. We're talking about the elbow. We have this elbow term. Again, there is some sign difference, which is maybe where, so here, like, yeah, I guess here they had a negative sign and they, so that's why I guess with the negative side, you're maximizing this, but of course, if you remove it, you have a loss term that you are minimizing now. And then going back to where I was, this was the derivation slide. I have to go back to where I was because that was in my appendix. So yeah, here, so that's where we were. We had our term, and then talking about the KL divergence. This is just a little bit about the KL divergence in case some of you guys are not as familiar with it. And it's just a comparison between two probability distributions, how they differ from one another. And there was this video that was kind of showing that, I guess as a KL divergence, as the two distributions are closer, the KL divergence goes to 0. And so that's just kind of review of that, because also another aspect is that a lot of the derivation does use KL divergence as well. Can I go to the next slide here? Oh yeah, the important part I wanted to point out was that with Gaussians, the KL divergence can also be calculated with a closed form expression, and we'll see that because of that we can simplify our math a lot more, as you'll see in the upcoming slides. So yeah, I guess in terms of this, yeah, we have some simplification here. And again, I think I have a slide to show that simplification if you want to see it. It was also in the appendix of the paper. It'd be nice if it was called distribution divergence something. Yeah, I think it was named after some people, so that's why it's called that. But yeah. Anyway, so we do have these lost terms that we can simplify with some math. I'm not going to go too much into it, but I do have a slide on that if you guys want to see it later on. But basically, we do have KL divergence terms, and now we'll see that we can simplify those KL divergence terms further. So we have these three terms. So we have L0, and then we have this LT minus 1. So this is basically for any t minus 1 step. So there'll be multiple of these terms, for each of the time steps, but they are all of the same form. And then we have LT. And so one question you might ask is, what is this Q xt minus 1 x depending on xt x0? Because here you can see that in this KL divergence term. And that's not something we talked about yet, because we know, of course, this is the regular probability distribution for the reverse process. Again, this is directly from the reverse process. This is, again, we were talking about that whole equation where with the independent assumption and the Gaussian distribution, we could get this as well. And this is just the prior that we have, which is basically a Gaussian distribution. So all these other terms we know how to define, how to calculate, but this term here we hadn't covered yet. So let's talk about that term. And basically what that term is giving us is, if we have the original image and a noisy image, then we can get the distribution for some intermediate noisy image. And this can be derived with Bayes' rule. And again, I have a derivation if you want to see it, but basically we can derive a Gaussian distribution with the following mean and variance. And of course, we talked about these alpha terms before. So again, these are terms that we can calculate. But if you look closely here, what we're basically doing is we have some sort of interpolation between x0 and xt. So basically, that's what it is that we have, our original image and our noisy image, and we're just trying to find a distribution in between. And of course, technically, we could get the distribution of we could technically get the distribution of xt minus 1 just conditional on xt. But there are many possible possible values for xt minus 1. So if we knew our x0, we could basically limit our estimate of xt minus 1 to more likely cases instead. So that this is what is known as a variance reduction term, because it's kind of like, in a bit, we're kind of cheating in terms of we're looking at, we have our forward process where we're kind of, diffusing from, the original image all the way to some sort of, I guess in this case, a noisy image. But we actually want some distribution of xt minus 1, but we're actually looking at the following step to see, what it should be, what kind of where it's going. So it's kind of a little bit of cheating in that respect, but we're able to do that for our trading process, and by doing so, we actually kind of reduce the variance, or kind of make our estimate of our distribution for xt minus 1 a little bit more accurate.
I have a question which is a little out of order, and so if you can't get to it right now, we can maybe get to it later. But I'm really curious how this variance reduction ends up. Is it in the simple loss where it's all about like the loss based on the noise? The like equation 14 in the DDPM paper.
Yeah, that's because it's used to derive that. Yes. because basically that is in this term here, and the simple loss comes from this LT minus 1. So yes, in a way, it's used to derive that.
Great.
I just asked Catherine if I'm on the right track with all these explanations or if I'm completely off.
That's one of the parts of the paper that I never understood, actually.
Oh, okay. Yeah, this is kind of my understanding. I don't know how accurate it is, but this is what I felt like, yeah, it's kind of just estimating in between so that we have, I guess, a more accurate estimate. Because yeah, I guess if you're doing these sort of these processes, there are definitely, I guess, many possible answers. But if we know kind of the final value ahead of time, then we kind of can limit it. So I think that's what's going on here. But yeah.
Yeah, I guess what confused me in particular is that variance reduction like uses the x0 in a way that like the simple loss as I see it, it's just based on sort of the xt image. But I don't really understand it.
Well, because I guess x0, I guess, yeah, I guess we just have to go through the derivation and see. Yeah, I'm not sure. Yeah, let's just go to derivation and see if maybe it clarifies it a little bit, but yeah, that's a good question. Because I don't know, because we use this mean term later on as well. So I guess, yeah, because I can't, I'm also like, as I walk through it, then I can remember. So if I walk through it, I'll try to see if I can get to that and answer that again. Anyway, let's see what we have here. So, oh yeah, I just wanted to recap the training objective a little bit more because it provides a little bit of more intuition of these training objectives. So the first term is sort of like a reconstruction term where, it's just like if we have the x1 is basically the last time step before we get x0, right? So it's just saying this is and you're minimizing the negative log likelihood of this. So just kind of saying, oh yeah, this model is producing appropriate x0. It's I guess producing appropriate images, and it's kind of, again, a similar sort of loss term. I think the loss term there's a similar loss term in the VAE as well. So it's, again, kind of taken directly from VAE. And then the other terms are this LT minus 1 term, which is basically saying, can we match the xt minus 1 distribution to the actual xt minus 1 from the forward process? So we have our reverse process here, and that's the process that we're trying to learn in terms of learning those Gaussian transitions, and we're just matching it to the forward process. Actually, that's all we're doing. We're trying to match it to the forward process. So we know the forward process. We can see how it's being, the diffusion process with the forward process, because that's all predefined. And then we have this this model that we're learning, and we just kind of match it to what we're observing at a particular time step. And then this term basically is saying, basically just saying I guess the final image that we get from the forward diffusion should match, or the distribution for that should match the prior distribution of the reverse process. And again, these are both supposed to be Gaussians, and it's supposed to actually, it's not really, this is a constant, really. So it's actually can be ignored, actually. So yeah. Let's see, moving on. I wanted to note that all of that applies for all diffusion models, or like a lot of the formulations of diffusion models have a similar sort of formulation in general. So if that makes sense, then yeah, yeah, it's, I guess, important that all of that makes, I guess, fairly makes sense. But then what we talk about next will be actually what is specific to the DDPM, because what happens is that DDPM makes some assumptions that simplify the math even further, and that's what we're going to talk about next. So I guess this is again another good time to stop for questions. Okay, if there are no questions, just I'll go over some of the additional assumptions that DDPM makes. One of the assumptions are basically all these variances are constants. So that's true, of course, true for the forward process, but also for the reverse process. So technically, you could have the reverse process have variances that are functions, again, a neural network. And there are some models that indeed do that. But for the DDPM, they just fix it to a time-dependent constant. In fact, they fix it to the same variance as what is in the forward process. So that's the kind of the main assumption with DDPM. And so what that means is that all we have to actually learn for our reverse process is just the mean of the Gaussian distribution. So all we're trying to do is come up with a neural network that can estimate the mean of that Gaussian distribution. Okay, so as I mentioned earlier, this LT loss term can essentially be ignored because we already defined this pxt to be an isotropic Gaussian. Basically, what that means is that we have a reverse process which is starting out from pure noise. That's what we define it to do. So what it means is that the distribution for x of t for the reverse process is an isotropic Gaussian. It's pure noise, Gaussian noise. And then again, we also already knew what this q of xt is based on the fixed forward process, and it's a constant. And also, if t goes to infinity, actually, those distributions will be similar enough that it will actually go to 0. Is that all correct, Kath? Is that all correct, Catherine?
I think so. Yeah.
Okay. Okay. Okay.
Number of time steps goes to infinity, and you don't scale down your betas accordingly as you increase the number of time steps. Eventually, if you diffuse for long enough with some schedule that isn't dependent on the number of time steps, you're going to get to a Gaussian.
Okay.
That's 0 mean standard deviation 1.
Right. Okay. Okay. Yeah. So, yeah, assuming you have the right, I guess, formulation, then yes, this loss term goes to 0. So basically, it just can be ignored. So we don't have to worry about it. But the one that I'm a little bit confused about, to be honest, is this L01 and how that is calculated, because apparently it's completely ignored. So Catherine, if you could maybe mention a little bit something about this and why it can be ignored, that would be really
the reason
helpful.
you could get away with ignoring it is that you make the betas for your first, second, your very low noise time steps, your starting time steps, you make them very small. And so the gap between time step 1 and time step 0 is made so small by picking the schedule in a way that you can simply ignore that, because it is a small gap, and so you don't have to care for visual quality.
Okay. So you're just saying it's just there's not much change that it doesn't matter. Okay.
Yeah, you just make the gap small by picking your beta schedule, similar to how you make the gap on the high end from t minus 1 from t minus 1 to t. You make that simply small by making your betas up there large, which is why the beta schedule starts small and becomes larger over time.
Okay.
To minimize the gap on both ends.
Okay. And that allows us to ignore basically both. Okay. That makes sense. Yeah. Okay. Does anyone else have any questions about this, I guess? Okay. Okay, then, yeah, I guess, yeah, those were, I guess we'll go to the more important terms, which is this LT minus 1. And as I was talking about, because there's a KL divergence of 2 Gaussians, and not only that, the Gaussians have this sort of constant variances, it can be simplified to a very simple closed form expression. where we just are taking the differences between the means of these two distributions, I guess the squared means of these two distributions, and then there's also a constant, of course, which we can ignore that constant for optimization purpose. So basically we get this very simple term because of all these assumptions that we make in terms of it being Gaussian and the variances, and all these assumptions give us this very simple term where all we're doing is we have an MSE loss between the mean of this reverse process and the mean of this forward process. So the neural network that we're training is just learning to predict the correct mean that we observe from the forward process. So that's what it's kind of showing. Basically, we're just trying to, we're starting out from the noise and going to going to an actual image by, with this reverse process, we're just trying to kind of match what we see with the forward process just in reverse. That's all we're basically doing. And so in order to do that, we are we're learning to predict the means. We're training our neural network to do so. Does that make sense? Okay, it makes sense. Then the next part is the sort of reparameterization. So again, technically, you could train with that previous equation, but I think the authors mentioned that this leads to unstable training. So
yes, because what happens is, if you actually do this, is your output of your neural network is going to be nearly the same as the input. When you have like numbers of time steps that you actually use in practice, which is like 1,000 time steps, then the difference between the mean at one and the mean at the next one is going to be quite small. So
okay, I see what you mean.
Yeah. There are a couple different ways you could reparameterize this, and noise prediction is the one in this paper.
Okay. Yeah. So the noise prediction is the one that this paper uses. So basically, we are defining our xt to be, again, this xt is a random variable, and we are defining it to be dependent, of course, on x0, and then we have this noise term, which is just, again, a variable that is sampled from a regular Gaussian distribution with mean 0, variance 1. And so this comes out, of course, from the, again, we defined earlier how we can just sample any arbitrary time step t. So that's just a kind of a different way of writing that out. But the important part now is that we can plug that in to some of these equations for example, for the mean. So here we have so yeah, again, here we have xt and x0. So we just define an equation for xt, and then we can get x0. So here we have xt, we just put that's what we have here, and then x0 is just basically just doing some algebra on both sides to get x0 from xt. So I think this is where I think there's a question here about where we have this x0, and I guess there was a question about that. And then here we just kind of make a new, we just rewrite that term for x0. And then what we can do is we can just do more math in terms of this, again, this mu tilde. We again wrote that equation down earlier, so we can just do some math to plug in these terms into that equation and simplify. And so then we just get this term for that instead. So that's a new term that we have. Okay. But again, we still do have, I guess, this sort of xt depend on x0 epsilon. So that's kind of, we just kind of want to yeah, it's kind of hard to work with that because again, that means like we need to have x0 at all times. So instead, we can make the noise a trainable function. So we're just making now the noise a function, and this is a function that's dependent instead on xt and the time step. So now we can plug that into the equation. So I think here, yeah, we have that here, and then we just plug it in here, and then we again do some more simplification. And so we plug it into the equation, and we get our we can redefine our function here and get this final objective. I think I do have the full derivation as an appendix slide again, so I don't know if you guys are interested in seeing that, but basically it's just a lot of math. And basically the important steps are we do these two reparameterizations where we're reparameterizing with xt, and then we reparameterize with this noise, saying that it's a learnable or a trainable function. Does that make sense? None of you guys have any questions. I'm a little surprised because all of this stuff like was confusing me when I first learned it. So I don't know. Okay, so
That thing before, the thing on the left of the on the other slide.
Oh.
Yeah. That thing,
yeah, this we can ignore,
that
right?
thing there. That's some sort of relative weighting term that. What does it do actually? It's relative weighting of time steps, right?
Right. Yeah, but I guess so that was gonna go to the next slide. They mentioned that they found better training without that term. But yeah, I guess it's relative weighting per time step. So like I guess yeah, because like if it's a weighting term, I guess it goes. I think it increases as time goes on. Is that right? I think.
I'm not entirely sure because in every implementation I've ever seen, they simply use the Wilson the next slide and leave that term out. So I don't know what the original relative weighting was before they simply drop it.
Yeah, I don't know, but I mean, I guess the weighting does have important role in terms of generally, I guess, like the weighting of this loss function term for different time steps can lead to different behaviors.
Since instead of training 1,000 separate models, one for each mean, we put them all into one model, essentially tying all the weights together. So
yeah,
it has to do with allocation of model capacity.
So yeah, that gives us the training objective where this is the kind of interesting training objective, because what we are training here is a model that basically we take so we basically are training a model to predict the noise, which is can be a little bit confusing, but basically what we're doing is we have, I guess, at a particular time step an image, which we could get this sort of noisy image with this term here. This is again the xt term. So yeah, we have we sort of like basically you can see the training here, the algorithm here. We take some random original noise, a random original image. So whatever image that we have observed, whatever samples that we have in our data set. So we select an image, and then we select a random time step. And then what we do is we calculate the noisy image at that time step. So that's what this equation is giving us. Xt. This is basically xt. And so we get the equation, we get the xt, and then we have that xt, and then we pass it to our to our neural network, which is this epsilon theta. And this neural network is supposed to predict the noise in the image. And basically, the idea is that this is really a denoising a denoising model, because basically you just take your noisy image and then you subtract out whatever noise this predicts to get us a the denoised image. And so that's what we're doing. We're training a model to predict the quote unquote noise, with this MSE loss term. And then when we're actually doing inference, that's what we're showing here. Again, we just calculate out xt and get this sort of predicted noise that we can subtract out of the noisy image to get us a more denoised image. And for sampling, of course, we're doing this. We have to do this throughout, starting from capital T all the way to 0. We have to go through each step to iteratively denoise the image. And so we just continually do this for, I guess, however time steps you have. And we're, we continue to remove noise according to this, whatever this neural network is predicting, to get us a fully denoised image, which is a sample from your estimated data distribution. Does that make sense? Because that's what it is. Let's see. This would be the best time to ask any questions you have about any of this stuff.
Can I ask a quick question in regards to step 4 in algorithm 2?
Step 4 in algorithm, yes.
Sigma sub t z, is that
yes.
extra noise that we're adding back in?
Yes, because this is like this is technically, what is it, I guess this is some sort of like sampling procedure where basically there's a different sort of formulation which I find is easy to understand, which is, I guess, mentioned in the paper, which is this sort of Langevin dynamics formulation. I don't know if you caught that, but basically it's like what we'll see, I guess, later on, maybe as we talk in the next couple weeks, is that what we're doing really is we're, I guess, figuring out the sort of the gradient of the probability distribution, and then it turns out that you can do this sort of sampling procedure if you know the gradient of the probability distribution, and you, I guess, there's some sort of adding of noise, then it allows us to sample from that probability distribution. So there's this sort of, it's called stochastic gradient descent with Langevin dynamics. I forget what it's called.
SGLD.
Yeah. So
that makes a lot more sense.
So yeah, there's, I think in the next week the paper we'll talk about would be this sort of score-based formulation, because I think that also makes more sense, because basically what's happening is that, this is kind of a spoiler for, I guess, the following weeks, but this sort of calculating, predicting of the noise really is getting us the gradient of the probability distribution, and giving us a function for the gradient of the probability distribution. And there's this sort of algorithm known as stochastic gradient Langevin dynamics, which says if you have that gradient of the probability distribution, you can then sample from that probability distribution, where you, I guess, we can, I guess we'll talk about that in the upcoming weeks, but that's why we have that, because otherwise, if you're just having the score of the gradient of the function, it's called a score. If you have that, I mean, you're just following that, you would just go to I guess the maximum of the probability distribution, which would just give you the most likely observation, which wouldn't be very helpful. So the noise kind of lets us explore, I guess, and sample from other parts of the probability distribution, if that makes sense.
Yeah, it does make sense. Thank you.
Give me one moment. I think I need to plug in my laptop. So just give me 1 sec. Okay, so this PowerPoint is not working, so I'm just gonna have to move once again. Sorry about that. Just give me a couple seconds here. Okay, I'm back. Can you hear me?
We can.
Okay, and you can see my screen and everything, so.
Mm-hmm.
Okay, so moving on. So there were some more questions here. Schedule of the, yeah, I mean, so there's a question about kind of how the schedule of the betas would change stuff. I think, yeah, we'll talk about that more because, like, yeah, different papers do use different schedules for the betas, and they have different effects. So I think when we get to some other papers, we'll discuss that. Like, I think, I don't remember which papers, was it like, there was like one paper I was reading recently that was talking about using a different schedule.
Was it the improved DDPM?
Yeah,
paper
yeah,
by
I think that was the
OpenAI?
one. Yeah, yeah,
They
yeah.
trade
The
their cosine
cosine?
schedule.
Yeah,
Yeah.
that one. Yeah. So I think, yeah, that'll be a paper we'll probably talk about as well at one point. But yeah, so different papers will do that, and it does affect, I guess, the visual quality of the images as well. So yeah. Okay. So I mean, we're almost kind of wrapping up here. Basically, the next one is just kind of the experimental setup in terms of the actual model. So the important aspect to realize here is the actual model is a UNet model here, where you're taking an input image and you're outputting, for example, you're outputting the denoised image. That's what you're doing. So because the input is an image and the output is also an image, they just use a UNet. But the important fact to remember is that this function also depends on the time steps. So they do specify the time steps with a sinusoidal position embedding, which is like similar to what you would see in a transformer in terms of they have position embeddings in transformers as well. So I don't remember exactly how that's specified, but it's inputted in there somehow. I don't remember exactly. Oh, and the time step should not be 100. It should be, I think, 1,000 actually.
It's
I
1,000.
think.
Yeah.
Yeah, that's
Everyone
a
uses
typo.
1,000 if they use like a fixed number of time steps instead of continuous.
Yeah, so that is a yeah, that was a typo on my end. But yeah, and in terms of the betas, in this case, the schedule is a linearly increasing schedule. And I guess for like some of the data sets, they have different augmentations, like the CFAR10, they I think mentioned a horizontal flipping. And then the optimizer that they used was Atom, and they also use exponential moving average for the model weights. And I think that's actually quite important. I think Catherine said that usually using
Yes,
EMA is
you should
very
basically
important.
always use it for this.
So I think that was just a footnote that they mentioned, but apparently it's a very important thing. So yeah.
If you do not use it, you will get quite bad results, and you'll wonder why.
Okay, yeah. So and then yeah, just some yes samples here. This is some of the samples that are produced, and then I guess their FID scores, for example, inception scores and FID scores. So I guess here, for example, their FID in this case for CFAR10 was, I guess, state of the art at the time, or I guess not. I guess for conditional models, for I guess unconditional. Sorry, for unconditional models. For conditional, I guess the StyleGAN2 was best for that, but still quite competitive at the time. And so I think that's kind of what sparked this whole diffusion model revolution, I guess. I think that was it for me in terms of the explanation of the mathematical model and the formulation. Does anyone have any questions?
Yeah, I was wondering what are there any like technical advances or mathematical advances in this paper compared to the original 2015 one, apart from the fact obviously that they applied it to images?
The advances were, I guess, I think there was like, again, I think the advances were some of those simplifications that they did in terms of the assumptions of the variances. Some of those assumptions, I don't think they were there in the 2015 paper.
Did the
And
2015 paper have anything like the L simple? Because that is the single,
yeah,
that's probably the single biggest thing in this paper that was responsible for the quality. If you simply look at that FID table, you'll see that the L simple model, this is the one that does way better.
But I think that's because the L simple model comes from those variance assumptions and things like that, and I don't think the other paper had those assumptions. I think that's what happened.
L simple also uses a different relative weighting of time steps, and I think that is also important.
Okay. Yeah, the DDPM paper does not talk about it much, except say they got better results without it.
Later papers went into this, such as variational diffusion models, and the Karras et al. Paper elucidating the design space of diffusion models.
Yeah. I guess the weighting term affects a lot of the visual quality, so it's
which is actually interesting because L simple is not the best for a log likelihood. If you're optimizing for log likelihood and optimizing for FID and visual quality are like they require two separate things, which is kind of a problem, but that's how it is.
That's right what the improved DDPM paper was talking about, right? They were trying to improve the log likelihood instead.
I remember the variational diffusion models went into it a lot, and that's mostly where I remember that discussion from.
Okay, I have not read that paper yet, so I have to read that as soon as possible, I guess. I read the improved one, and the DDIM and the Karras et al. I remember the Karras et al. Was also talking about the weighting term. But yeah, were there any other questions about this? Because this is very, I know this can be very confusing. This is again like the sort of, I guess, what is like referred to as the likelihood formulation, I guess. But then there's also the score-based formulation, which is I think we'll talk about next. I think that is maybe easier to understand. At least I found it easier to understand, so I think we'll talk about that next.
This might be like, I don't know, kind of a naive angle on this, but is it just me, or does this loss kind of look like what we're doing is massive data augmentation of like these pairs of like a noised and then one more step noised images? And that's like just like you've kind of created that data and now you're just trying to map from like one to the other, or to the noise.
Yeah, I mean it's just kind of it's like a denoising autoencoder, or like a denoising it's just a denoising algorithm. That's what it is, I guess.
It's an image restoration network. Yeah. You can that's specialized in Gaussian noise.
Yeah. I looking at this, I thought in a very similar way. Like, do you think? I guess this is a question, but it's related. Do you think that there's a place for this, maybe in like a self-supervised setting, like this? It kind of feels like this could be placed maybe within like a, I don't know, like BYOL type model or data vector or something.
For which now?
As like the encoders, and applying the different augmentations.
Oh, maybe. I've definitely done things like train diffusion autoencoders where in other words, you had a regular encoder and then a unit diffusion decoder, and it would learn to put diffusion loss, the reconstruction loss there was sufficient to like get meaningful things into these small latent.
Mm-hmm. I guess the other thing was like, I guess the recent paper showed that you don't even need like necessarily Gaussian noise, and like, yeah, I haven't actually read that paper in detail. The cold diffusion? Yeah.
Yeah, I thought most of their results were really blurry, but it was like impressive that they got them at all.
Yeah. Because that's the thing, like a lot of the math comes directly from assuming everything is Gaussian. So when they do stuff like not Gaussian, I don't know how that works.
Oh, yeah. Gaussian noise as a degradation has a lot going for it, I think. Also, the math doesn't need to be as complicated as it is in this paper, I think.
Okay.
Later papers have simplified it. But
I was wondering. Paper came out like 8 days ago, cold diffusion, and they basically did some stuff showing that you don't even need any noise at all. You can just like do Gaussian blur, or even do kind of other weird algorithms like pixelation or something, which kind of maybe challenges the existing perspective a little bit.
yeah, the fundamental thing that these models are doing is they're letting us sample from a highly complicated multimodal probability distribution with many different modes, using a model output that is a unimodal probability distribution by iterative sampling. Every time step in the reverse process is a decision point where you can go from the mode you're in into many other modes, and therefore sample from your multimodal distribution. The noising process is just a way to accomplish this accomplish training this model with a simple convex loss, such as mean square error. You can do other degradations as well that seem to work, except you seem to get blurry results doing it. So.
Yeah, that's a good summary of that. Like, yeah, going, I guess, yeah, from a unimodal distribution and, well, yeah, I guess is it like you could consider like I think you may have mentioned this before, like a mixture of Gaussians. Like you have you're starting out from one Gaussian and then you just, yeah, like the Phi distribution, just assuming it's like a mixture of Gaussians, and then I guess you're
the actual data distribution is a mixture of Gaussians. Yeah.
Yeah.
That is the distribution of the data once perturbed by noise. Well,
okay.
Rather, not the data distribution, the distribution of your training set once perturbed by noise is a mixture of Gaussians.
Right. And I think that makes sense once you look also at the, like the, was it the denoising score matching or whatever they, like, because it's like, what is it they call it? You have that sort of smoothing kernel or whatever, or I guess what it's called. Yeah, and so that you just, what is it called? Kernel density estimation kind of thing.
Except we never actually get the density. We never even get an unnormalized density. We only get its gradient at that point.
Mm-hmm. Right. But yeah, we'll I guess get through some of these other papers that maybe make more sense. I think we'll talk about the score matching stuff more. I think that'll be the next thing to talk about, because that might make more sense. But yeah, if there are no other questions,
I have a quick question. Sorry.
Okay, yeah, for sure.
Just in regards to the implementation. So for example, in step 2 of algorithm 1, we're pulling X naught. For example, if that's an image, are we flattening that image down to one-dimensional? Or is
the image is just passed in, it's just as is passed into a UNet. So just like you would see with any sort of image to image task, because here we're just going from a noise, or I guess from, in the case of the forward process, we're going, well, in this case, yeah, we take the image and then we add noise to it, And so we have this noisy image, and then we take that noisy image and pass it into our UNet model to get a denoised image. If
Okay.
that makes sense.
The input
you.
and output shapes of a unit are typically the same or quite similar.
Got it.
Okay, so something. Yeah, and then Q of X naught is just a sample from data set. So yeah, all 2 is saying is just fancy notation for saying get an image from the data set. That's all it is. And then 3 is just a fancy notation of saying just get a random time step. 4 is just saying just get noise. And the noise, of course, will be same shape as the image so that you can add it to the image. So it's just that would also be like a, I guess, whatever shape the image is. And then 5, of course, you have your loss term. And again, there's that term in the middle that is giving you xt, which is your noisy image. You pass it into the model and you compare it to, and the model is predicting how much noise, and you're comparing it to actually how much noise you did add to the data set, or to the image.
Another thing this algorithm one leaves out that you really want to do in practice is to use a large batch size, and do not try this with one image at a time. It will go badly.
Okay, I did not know that. Well, I guess when you mean large batch size, like what is like 32, 64?
I do like 512 or larger these days.
Oh,
mini
wow,
batches
okay.
of that size, you can do it with smaller.
Wait,
but
I think the paper used like, didn't it use like, I think it used like 32 or 64, no?
Really, did it?
Let me check.
In practice, I've seen it go better as I increase the batch size, is why I bring this up.
It was in the appendix somewhere here. Where was it? We tried Atom. Oh, 128 for CFAR 10 and 64 for larger images.
And they didn't try anything else.
Yes, they said we did not sweep over these values.
I've seen
So that's
things
what they
go a
used.
lot better when trying, say, 512 versus say 64. As in things you will mistakenly think that techniques that you have tried, research techniques that you're now attempting to, don't work when they do work, if only you had sufficient batch size. And the reason for this is just that the loss is really noisy and the gradients are really noisy too.
And that's also why we use EMA, right?
I think so, yeah.
Okay. Yeah, I'll try to put like a quote. I'll see if I can get a quote example to put up. And yeah, see if I guess yeah, probably something on CFAR 10 or I don't know. We'll see. Interestingly, they did use a TPU to train all these models. So, but I don't know. Did they use it? I don't know if they use it. Like, I mean, some of these models, like CFAR, is like pretty small images. I don't know why they needed a TPU.
They're Google. They probably just had a TPU.
This is, I don't think so. This is UC Berkeley, right? Yeah.
Wow, didn't he join Google Brain later, or am I mistaking it for a different person?
He may have joined after this, probably. Yeah, I don't know. This was said. This is UC Berkeley, and then it also said that they got it from the TensorFlow Research Cloud TPU access. Said in the acknowledgments. So, yeah.
He did go to work for Google after that, so yeah.
Okay.
they got free compute, and that explains why it was TPU.
Okay. Okay. Is this observation specific to diffusion, or is it applied to transformers, etc.? In terms of the grade, the larger batch size. I mean, that's kind of a general discussion about like larger batch sizes, or I mean, I guess I don't know. This is probably something specific to in terms of like diffusion models having noisy gradients. That's why we need larger batch sizes. I guess I don't know about like the transformers if they. Yeah, it depends on that, I guess. Yeah. Okay, so I guess in terms of next week, does anyone want to present like one of the score matching papers, or do you just want me to continue presenting this one, the next paper? Because yeah, I mean, yeah, totally would. I mean, we can also discuss over the chat. I'll put the link to the paper that we'll talk about. So it seems like this took about 1.5 hours. Maybe I'll also see next week. We'll keep it at 1.5 hours, maybe, if that works well for everyone. I think, yeah, probably, yeah, I think we lost like 10 minutes because of like all these technical difficulties. So, but yeah, I guess that is it. I will put the I'll see, I think the recordings, I might like try to upload it to YouTube and put a link in the chat. I will upload the PowerPoint. Again, feel free to ask any questions. But yeah, that's it of this. And then, yeah, I was actually going to ask Catherine some additional questions, but but I'm stopping the official recording, I guess. So.